I certainly have many happy I certainly have many happy memories of scientific interactions with Ludwig, including the time when I visited in St. Petersburg in the spring of or winter of 1983. So as you can see, my talk is about scale invariance, conformal invariance, and Ricci flow. And I was trying to make a talk that would be interesting from different points of view to different members of the audience because I imagined there are quite diverse interests in the audience. So going back to 1975, Polyakov was the first to seriously consider what's called a nonlinear sigma model in 2 dimensions with a curved manifold as a target space. He took the target space to be an n-sphere with a round metric. And so the sphere, I'm assuming you can see my cursor here. The sphere is described by the standard equation for real variables xi, but Polyakov promotes the x's to fields on a 2-dimensional space and take the action to be this one. It's a 2-dimensional version of an action that would describe geodesics on the sphere. It instead is a quantum theory that describes harmonic maps from a 2-manifold to the sphere. Polyakov made, this was very soon after the birth of the standard model and the discovery that gauge theory in 4 dimensions is asymptotically free, which fundamentally changed the way its quantum properties are understood. And physicists at the time were trying to grapple with that rather difficult problem in 4 dimensions. Polyakov discovered that this simpler looking model in 2 dimensions has the same property of asymptotic freedom, leading to many of the same questions. And the analogy that he made between sigma models in 2 dimensions and gauge theory in 4 dimensions was very influential. Asymptotic freedom means that under the renormalization group flow to the infrared, which means to long distances, the coupling constant lambda effectively becomes bigger. So this theory can be studied semi-classically if lambda is very small. Lambda being small, you might think of lambda as being h bar. Lambda being small means that we're near the classical limit. The action is big, and fields that are not close to the extreme of the classical action, which are classical solutions, are strongly suppressed. Polyakov showed that under renormalization group flow to the infrared, lambda becomes bigger, meaning that the classical approximation is worse. Conversely, in the ultraviolet, the classical approximation is better and better. That's called asymptotically free. So this simple result about the renormalization had 2 consequences, just as in 4-dimensional gauge theory. First, you can convincingly, although not mathematically rigorously at the present time, argue that the model exists as a bona fide cutoff independent quantum field theory. So good news, the model exists as a true quantum field theory. But B, it's very difficult to determine its physical properties, because the physical properties have to do with how the solutions of the equations behave at long distances. But the renormalization group equation tells us that at long distances, the coupling parameter lambda is effectively becoming big, and we lose control. So we learned that the theory exists quantum mechanically, but by the same token, we learned that it's going to be difficult to understand it rigorously. Now, 5 years later, Dan Friedan, whose advisor was Isidor Singer, generalized the problem drastically. Instead of considering a simple target space with a simple Riemannian metric, he considered a completely general Riemannian manifold W as the target with any Riemannian metric Gij. So the action is this one, which generalizes, well, it describes harmonic maps from a 2-manifold to any target. It's an action that's conformally invariant at the classical level, which I should have stressed for Polyakov's example. Polyakov's model is the special case that the target space is a sphere of radius 1, and the metric is 4 pi over lambda times the round metric of the sphere. Friedan computed the one-loop approximation to the renormalization group flow. So first of all, in a rather elementary way, he showed that the renormalization group flow perturbatively, and he computed only the leading perturbative approximation. He showed that the renormalization group flow will involve a local function of the metric. And in the leading order, he found that the renormalization of the metric is by -2 times the Ricci tensor. I'm not using exactly Friedan's normalization. For example, if Rij is positive, the metric becomes smaller as t increases, which generalizes Polyakov's result that lambda becomes larger in the case of a round sphere. So a large metric on the target space, a large metric means that the semi-classical approximation is good. A small one means it's bad. So this generalizes Polyakov's discovery that at short distances, the semi-classical approximation is good, which enables you to argue that the model exists quantum mechanically if Rij is positive. But at big distances, again, assuming Rij is positive, the quantum properties are difficult to understand. Now, by coincidence, the same equation describing the, quote, time, unquote, evolution of a family of Riemannian metrics on a manifold was introduced by Richard Hamilton at about the same time. I want to stress that for Polyakov or Friedan, T was not time. T was a renormalization group parameter that measures the typical length scale at which you're making observations. For Hamilton, T was more like time. Hamilton, of course, was not studying quantum field theory. He was hoping to prove the Poincare conjecture by using the Ricci flow equation to evolve any initially chosen metric on a three-manifold W to a simpler one that could be used to analyze the topology of W. Now, going back to quantum field theory, in general, it's important to understand the fixed points of the renormalization group, which correspond to theories that are unchanged when one increases T. That is, when one probes the theory at longer and longer length scales. This is important in relativistic field theory because the fixed points give important qualitative information on the behavior of any theory. In statistical mechanics, the fixed points are important because they correspond to critical points, like the critical point of a fluid at which the behavior qualitatively changes. Now, in Friedan's case, since the renormalization group equation is this Ricci flow equation, naively, a fixed point of the renormalization group is a Ricci flat metric. In other words, a metric that satisfies Rij equals 0. But as Friedan observed, in general, we should only care about the metric of W up to diffeomorphism. And therefore, if the change of the metric G under changing T can be interpreted as the result of a diffeomorphism, then this is a fixed point in a more general sense. While the assertion that dg dt is the change in G induced by some vector field V, the generator of a diffeomorphism, would be this, which is equivalent to the renormalization group flow if the Ricci tensor can be written this way. So Friedan interpreted that equation, which is more general than the condition for Ricci flatness, as the general condition for a fixed point. Now, Hamilton was also interested in this general equation for a fixed point, which he called the Ricci-Soliton equation. Hamilton also needed a more general Ricci-Soliton equation with a cosmological constant, which appears hard to interpret in the sigma model. Ricci-Solitons, that is, solutions of the Ricci-Soliton equation, were important for Hamilton because singularities generated by the Ricci flow were the main difficulty in carrying out his program to prove the Poincare conjecture, and Ricci-Solitons control the behavior near singularities. Actually, Hamilton showed that singularities are associated to ancient solutions, solutions for which the time of the flow can be started at -infinity. This condition of an ancient flow is very important physically. For physicists, ancient flows correspond to asymptotically free theories that are expected to really exist as cutoff-independent quantum field theories, though mathematically this is an unproved conjecture. A prototype of an ancient flow is Polyakov's renormalization group, or Ricci flow, in the case of a round sphere. And this was also an important example for Hamilton. He described it as a round sphere that flows to a point. It collapses to a point at finite time. From Polyakov's point of view, the collapse to a point means that the semi-classical description completely breaks down. By 1984 and 5, this renormalization group flow of Riemannian metrics was important in string theory. It was understood by several authors that a special case of the Ricci-Soliton equation in which V is a gradient, V is the gradient of phi for some real valued function phi on W, corresponds to a classical solution of string theory in the one-loop approximation. So the classical equations of string theory were not the Ricci-Soliton equations. They are a more restrictive version of the Ricci-Soliton equations, in which V has to be a gradient. So in that case, the generalized fixed point or Ricci-Soliton equations becomes this one. And that's the field equation derived from string theory at low energies if the only fields considered are the metric G and the dilaton phi. I should have said that phi is the dilaton of the string theory, usually called. In the mathematical literature on the Ricci flow, Ricci-Solitons of this kind are called gradient Ricci-Solitons. So what's a concrete example of a gradient Ricci-Soliton? For example, the two-dimensional black hole, which can be viewed as an SL2R mod U1 coset. At the low energy approximation, that's an exact description of a conformal field theory, the SL2 mod U1 coset. But at low energies, it's equivalent to a Ricci-Soliton. And that is an example that Hamilton would have called an ancient flow. The flow could start at time minus infinity. So the conjecture says that there should be an exact conformal field theory associated to this flow. And in the particular case of the two-dimensional black hole, we know what it is. It's an SL2R mod U1 coset. So there's a big mathematical literature on gradient Ricci-Solitons, which for string theorists are the Ricci-Solitons that correspond to classical solutions of string theory. Now, the string theory interpretation motivated also in the mid-80s a generalization of Friedan's work in which we include a two-form field, usually called the B field. So the B is a two-form, it's anti-symmetric in I and J. So there's a term that you can put in the two-dimensional action similar to this one, but different. Because B is anti-symmetric, we need an anti-symmetric tensor on the two-manifold, the Levi-Civita tensor. And this leads to what in some recent mathematical literature is called the generalized Ricci flow. In other words, the renormalization group, the one-loop renormalization group flow for such a model is the generalized Ricci flow, which is the topic of a recent mathematical book by these authors. So everything I've said till this point has a generalization in this context. Now, the importance of gradient Ricci-Solitons in string theory depends on the following, which I'll state for simplicity without the B field, and which was elucidated in this period by various authors. A general solution of the fixed point equation corresponds to a scale invariant quantum field theory, while a gradient solution corresponds to a field theory that's conformally invariant. So conformal invariance is the condition for a classical solution of string theory. That's why this is the right. That's why the stronger condition, which I'm having trouble highlighting, but I'm trying to, above this word I can highlight. The stronger condition is the condition for a classical solution of string theory. I'll elaborate a little bit on the relation of conformal invariance and scale invariance. A Lorentz invariant quantum field theory has a symmetric tensor T mu nu, which is called the stress tensor also. It's conserved in general, but conformal invariance means that it's traceless. So we take the trace using the Minkowski space metric eta or Euclidean signature. We'd use the Euclidean metric, the Kronecker delta. If these properties are satisfied, you can find that for any conformal killing vector V mu, satisfying this condition, there is a corresponding conserved current. So if you merely had conservation of the stress tensor, any true killing vector, meaning one for which the right-hand side is 0, would give a conserved current. And then the killing vectors would generate a symmetry, which would be the automorphism group of the isometry group of the Riemannian manifold. But if the stress tensor is traceless, you're allowed to consider conformal killing vector fields where the right-hand side is not 0. And then you can get a more general set of conserved currents for such killing vector fields. And you'll find that when you verify conservation, you'll need to use the fact that the stress tensor is traceless. So when the stress tensor is traceless, the theory is conformally invariant, meaning it's invariant under the conformal group, which is the group generated by the conformal killing vector fields, not just the true killing vector fields. Now, scale invariance means that the trace of the stress tensor is not zero, but is the divergence of a current for some S mu. In such a case, one does not have conserved currents associated to arbitrary conformal killing vectors. But there is such a current in a very important case of the dilatation generator, which is the generator of an overall rescaling of space and time. So K, which generates an overall rescaling of space and time, is associated to this conserved current in case the trace of the stress tensor is the divergence of some S. So a short calculation will show you that this J is conserved, provided T is conserved, and also this is true. The theory is then said to have global scale invariance. And global scale invariance, naively, is the condition for a fixed point of the renormalization group, because the renormalization group has to do with the change of the physics under an overall change of scale, which corresponds to this overall rescaling of the coordinates. So it's not at all obvious why fixed points of the renormalization group would be associated to anything more than global scale invariance. It's actually a rather deep result that you should get more than global scale invariance. Polchinski elucidated these matters in a paper in 1988. Sorry, I should say that the conjecture that scale invariance at least often leads to conformal invariance was initiated by Polyakov and others back in the 70s. But jumping ahead, Polchinski gave a more precise account in 1988. Well, first of all, he explained what I just explained, but he also had two further results. First, he proved that in general, in two dimensions, for unitary quantum field theories with a discrete spectrum, scale invariance always implies conformal invariance. In the context of sigma models, the hypothesis of a discrete spectrum means that the target space is smooth and compact. So it's a natural class, but you might be interested in sigma models with, for example, a non-compact target space. Now, Polchinski's statement was just in two dimensions, and the generalization above two dimensions proved difficult. But eventually, an argument was found in 4 dimensions. In 3 dimensions, let alone above 4 dimensions, this relationship is an open problem. Polchinski's general argument in 2 dimensions showed that the problem is closely related to the Zamolodchikov C theorem. The Zamolodchikov C theorem deals with the following question: is the renormalization group flow irreversible? For example, in the one-loop approximation to a sigma model, the question is, does the Ricci flow equation have solutions with non-trivial t dependence that are periodic in t? That's a special case of the question of whether the renormalization group flow is irreversible. Saying that it's irreversible would say in particular that there are no periodic solutions. So back in the 70s, well, I first heard about this question at Lesuche in 1975. Intuitively, physicists suspected that the renormalization group flow should be irreversible because intuitively the renormalization group flow has to do with integrating out high energy degrees of freedom to produce an effective action for low energy degrees of freedom. And the process of removing from the description some high energy degrees of freedom, one might naively expect it would be irreversible. However, a proof was difficult. Zamolodchikov in 1986 had given the first concrete result. He gave an abstract argument that showed that the renormalization group flow for unitary quantum field theories with discrete spectrum is irreversible in 2 dimensions. Again, the analog in higher dimensions was more difficult, though here by now there are answers in 3 and 4 dimensions, but not above. Polchinski adapted Zamolodchikov's argument to show that scale invariance in 2 dimensions implies conformal invariance, given a discrete spectrum. I won't explain the arguments of Zamolodchikov and Polchinski, but I will show that the two questions about irreversibility and about the relation of scale invariance and conformal invariance are closely related in a different context involving the Ricci flow. Polchinski did something else. So this was a somewhat abstract argument, but for a sigma model constructed from the metric only, Polchinski found, well, he adapted something that had been found in the 70s by Bourguignon. Polchinski found that for a sigma model constructed from the metric only with a compact target space, there actually are no Ricci solitons at all, no non-trivial Ricci solitons. Bourguignon had shown that for a compact manifold, if there's a vector field that satisfies this equation, then V is a killing vector field, and therefore the manifold is actually Ricci flat. So Bourguignon's motivation, I won't explain what it was, but it was different from the motivations of either Friedan and quantum field theorists and string theorists, or Hamilton and three manifold theorists. Now, recently with Papadopoulos, I revisited these questions using arguments that go back to Perlman as part of his work completing Hamilton's program and proving the Poincare conjecture. And our starting point also involved the work of Olenek, Sunita, and Woolgar, who adapted Perlman's construction to include the B field. So why did we revisit the subject? There were various motivations. Polchinski's abstract argument wasn't too illuminating about what happens in sigma models near the classical limit. I wanted to understand that better. His concrete argument using Bourguignon's result, which is useful near the classical limit, didn't generalize to include the B field, and also it was limited to the one-loop approximation to the sigma model, and it seemed interesting to have a more robust argument that wasn't limited to one loop. So there were various general motivations for this work. And I wanted an approach that, for example, would help understand the case that the sigma model target space is not compact and smooth, and would include the B field and give information to all orders, not just at one loop. So those were general motivations for this paper. But there also was a concrete motivation that I'll explain at the end of the talk, but after explaining what Papadopoulos and I actually did. So I want to recall the starting point of Perlman's series of papers on the Ricci flow. His series of papers began with a new proof of the Zamoljikov C theorem in the context of sigma models. But why was he interested in the C theorem? The idea of Hamilton's program, as I've told you, was that under Ricci flow, the metric should evolve toward simplicity, after removing or evolving past some singularities that may develop. That couldn't happen if the Ricci flow had periodic solutions. If the Ricci flow had periodic solutions, you'd go around and around and never evolve toward simplicity. So periodic solutions would be an obvious obstruction to Hamilton's program. So Perlman's first paper actually begins by proving that the Ricci flow is irreversible, and in particular, it has no periodic solutions. Irreversible means that he found what physicists call a C function, a function that is strictly decreasing under Ricci flow. I'll explain the generalization of the argument by the authors I called OSW, Woolgar et al., to include the B field. So here I've written the usual one-loop effective action for the fields, the metric, the B field, and the dilaton in string theory. I've written it in Euclidean signature, and I've written it in terms of H, which is the field strength of the two-form field B. So H is the three-form dB. Now, a first thing to note is that the kinetic energy of phi has the wrong sign. That's not true for the other fields. The kinetic energy for B obviously has the right sign because this coefficient plus 1/12 is positive. It's a little bit less obvious that the kinetic energy for the metric has the right sign, but a minus sign actually is the standard sign for the Einstein-Hilbert action in Euclidean signature. It comes by analytically rotation to Euclidean signature of the Lorentz signature Einstein action with the sign that leads to the energy being positive. So the other fields have the right sign, but the metric has the wrong sign. Now, you might think that the wrong sign metric makes the theory unphysical, but before you conclude that, you should remember that Einstein's action and Euclidean signature has the same property. So as I said, the action is this thing with a minus sign. And it's not in Gibbons and Hawking had shown in 1978 that this action has a mode with the wrong property. If you write the metric as some fixed metric times a Weyl factor e to the 2 phi. So you put the conformal geometry in G0 and the volume form in phi. They showed that phi has a wrong sign kinetic energy, which is one of the reasons that to this day the Euclidean path integral for gravity is not well understood. Now, I told you that this was the right sign, and indeed you can't fix things by changing the sign. If you change the sign, then this one mode would have a kinetic energy of the right sign, but then G0, which has a lot more modes, would have the wrong sign. So the right sign, the standard sign, is the one for which there's only one bad mode in pure gravity. Now, in the string theory version, we've added a field that obviously has the wrong sign, but we actually have not made it worse. If you work out the kinetic energy for the two fields, capital phi and little phi, you'll find that the kinetic energy for these two fields has signature 1, 1, with only one negative eigenvalue. So in fact, the situation is not worse than it was in pure gravity. It's the same. What's different is that in pure gravity, the wrong sign is somewhat hidden, but here the wrong sign is obvious. Now, in Einstein gravity, Gibbons, Hawking, and Perry suggested to deal with the problem by a Wick rotation of phi, which roughly, well, the starting point of the Wick rotation would have to be to maximize the action of a function of phi instead of minimizing it. Now, whether this is, or to what extent this is a good idea in gravity is still unknown today. Carrying this idea over to string theory, you might arrive at Perelman's idea of roughly maximizing the action of a function of as a function of phi to obtain a well-behaved functional of the other fields. To understand in what sense we can maximize the action as a function of phi, we note, following Perelman as elaborated by later authors, that we can write the action this way, where what I'm calling delta squared is the Laplacian, but the Laplacian defined to be negative definite. Well, often a minus sign is included to make the Laplacian positive definite, but I'm not doing that. However, the minus sign is explicitly in the action. We cannot usefully maximize S as a function of phi because the maximum would be at phi equals plus or minus infinity. What works better, as Perelman showed, is to maximize S under a constraint that the generalized volume is 1. We incorporate the constraint with the Lagrange multiplier. So we write the action, we write an extended action, which is this thing, with S, minus the Lagrange multiplier term, where the Lagrange multiplier is going to impose the constraint that the generalized volume is 1. So the extended action can be written this way. And extremizing it with respect to phi and lambda, we learn that e to the minus phi is an eigenfunction of an effective Schrodinger operator with eigenvalue lambda. And moreover, e to the minus phi is normalized. Its norm in the standard Hilbert space metric is 1. And obviously, e to the minus phi is positive. Well, something we know about Schrodinger operators on a compact manifold, let's say to make so that the spectrum is discrete, is that there's a unique non-degenerate ground state eigenfunction, which moreover is positive. And it's unique if you ask for it to be normalized. So the critical point with respect to phi and lambda that obeys these equations exists and is unique. And it's always a maximum rather than a minimum of the original action, because phi appeared in the action with the wrong sign. So to summarize what I've said, a positive normalized eigenfunction of the Schrodinger operator always exists and is unique. And so the extremum of S prime is unique, and moreover is a maximum of phi under the constraints. Well, before I go on, since I made the analogy with pure gravity and with phi corresponding to the Weyl factor of the metric, you could ask whether Gibbons, Hawking, and Perry, in suggesting the Wick rotation, should have started by maximizing the action with respect to phi. I actually believe that that would have slightly improved their presentation. But you would need to maximize the action under constraints. And in that case, the natural constraint would be that the total volume is 1, rather than this generalized volume in the string theory case. And maximizing the action under the constraint leads to something called the Yamabe problem. The Yamabe problem has a very rich theory, which is well developed. But the answer isn't as nice as Perlman found. Perlman found that the solution was always exists and is unique. For the Yamabe problem, the solution always exists, but it's in general not unique. So I don't know whether the solution of the Yamabe problem is as nice a starting point as one would want for pure gravity. But Perlman's approach works well in the presence of the dilaton. Now, for Perlman's proof of the C theorem, well, first we maximize the action as a function of phi to get a functional that depends only on G and B. I should have written that on the slides. I didn't explicitly, but the function we're going to study subsequently is what I'm calling S prime, which is the maximum with respect to phi under the constraint, or equivalently, it's the maximum of the unconstrained problem with respect to phi and lambda. Sorry, the extremum with respect to phi and lambda. Now, so what I mean by S now has been maximized with respect to phi under the constraint. Now, if I vary phi with respect to G and B, keeping fixed the generalized measure, this thing, I need a minus sign. There's a minus sign here missing in the way I've written the formulas later. Well, you get some formulas that you can write in detail like this. Sorry. That's the variation with respect to G, and here's the variation with respect to B. But more briefly, what you get is e to the minus 2 phi hat, where e to the minus 2 phi hat is defined here, but with the wrong sign, times the beta function of the sigma model. So these functions are actually the one-loop beta functions of the sigma model as computed in the mid-80s by authors I mentioned before. Remember, the beta function is what occurs in the generalized Ricci flow. There's a similar formula for the variation with respect to phi, but we won't need it, as we'll be evaluating the action at the maximum with respect to phi, where the variation is 0. Now, an equivalent statement to these, and a shorter way to write it, is that if you make any variation of G and B, keeping phi hat fixed, the variation of S is this simple expression in terms of the beta functions. So that was originally discovered in the one-loop approximation, but it was eventually proved to hold true to all orders. Now we can complete the argument for the C theorem using the renormalization group equations to tell us what we should use for delta G and delta B. The renormalization group equations say that dg dt and db dt are minus beta G and minus beta B, with the same functions beta G and beta B that occur here. This one should be beta G, sorry, another misprint. So if I differentiate the action with respect to t, and I use the fact that dg dt and db dt are this, I learned that the s dt, keeping fixed, evaluated at the constrained maximum with respect to phi, is this. That's strictly negative unless beta G and beta B vanish. In other words, it's strictly negative except at a fixed point of the renormalization group. That's Perlman's version of the C theorem as generalized to include the B field. S is strictly decreasing along any non-trivial flow, and in particular, there cannot be periodic orbits. Well, the nature of this argument is that it so unlike the argument Polchinski gave where he cited Bourguignon, this argument included the B field, but it also automatically extends to higher orders in sigma model perturbation theory. All that we needed to know is that the action has a unique extremum as a function of phi, keeping fixed G and B, and that the variation of the action with respect to G and B, keeping phi hat fixed, gives the beta functions. The second statement is sometimes called the Cauchy-Pafuti relation, and the first so it was proved in the 80s in particular. The first statement is automatically true to all orders of perturbation theory, given that the extremum as a function of phi exists and is unique and non-degenerate at leading order. So from the standpoint of sigma models, this is a rather robust approach to understanding the C theorem. But I told you that Polchinski had discovered that the problem of deducing scale invariance from conformal invariance is a close cousin of the C theorem. So how can we extend this Perlman argument to prove that scale invariance implies conformal invariance? Well, conformal invariance means the beta functions vanish, but scale invariance means they vanish up to the combined effect of an infinitesimal diffeomorphism generated by a vector field V and a B field gauge transformation generated by a one-form lambda. So generalizing what Friedan said, this is the condition for scale invariance. Well, yeah, okay. I think what I said is okay. Because Friedan called this, he didn't have the B field, so he didn't have this condition. He called this the condition for a fixed point. The fixed point in general is supposed to give scale invariance. Conformal invariance is more than a fixed point. And I explained that to get conformal invariance, V should be a gradient. And there's a more general version of that statement with lambda included. Well, the more general statement is just that lambda should vanish. So V being a gradient and lambda vanishing is actually the condition for conformal invariance. To prove that scale invariance implies conformal invariance, all we need to do is to use the fact that S is invariant under diffeomorphisms and B field gauge transformations. So I had a completely general formula for the variation of S under any change of G and B. It involved the beta functions. Diffeomorphism and B field gauge invariance says that this expression vanishes if delta G and delta B are whatever they would be under a diffeomorphism and gauge transformation. So inserting that, well, this is, inserting that, I get this, well, this expression being zero. Well, in general, this expression being zero is the statement that S is invariant under diffeomorphisms and B field gauge transformations. But using the relation of delta S delta G and delta S delta B to the beta functions, we find that invariance of S is the statement that this thing vanishes. Now, if we substitute in the condition of scale invariance, I'm missing also a zero on the left-hand side here. We learned that zero is equal to this expression on the right. So that implies that the beta functions vanish, and therefore in this framework, scale invariance implies conformal invariance. So all we did was to start with the fact that S is diffeomorphism and B field gauge invariant. That says that something, the variation of S, is zero, but in more detail, it says that the right-hand side is zero. And then using the relation of delta S to the beta functions, this was zero. And therefore, scale invariance says that the beta functions are equal to these expressions, or equivalently that these expressions are equal to the beta functions. So scale invariance tells us that the sum of squares of the beta functions vanishes, and therefore the beta functions themselves vanish, which in this framework is the condition for conformal invariance. So this completes what I'm going to say about, well, the relation of Ricci flows to sigma models and the relation of scale invariance to conformal invariance. So in the rest of the talk, well, as I said at the beginning, at the beginning, I explained some general reasons for looking again at the relation between scale invariance and conformal invariance, but I also mentioned there was a more specific reason for my interest. So in the rest of the talk, I will explain the more specific reason, but maybe I'll stop here for a moment in case there are questions on what I've said about scale invariance, conformal invariance, Perlman, and the Ricci flow.
Can I ask a quick question?
Yes?
Somewhere in the formulas, this homological metric was hidden, and I was following indices up and down, and I missed, but it is there, right?
Well, where it was hidden was when where it really was hidden, where I really hid it, was where I kept phi hat fixed rather than phi in the derivations. So the reason it's not straightforward to prove monotonicity of the Ricci flow is that the Einstein actions naively are gradient flow equations with respect to the Einstein-Hilbert action, but that's a gradient with an indefinite metric. And Perlman's maneuver of integrating out phi replaces the indefinite metric with a positive one, but it becomes positive when you keep phi hat fixed in the subsequent variations. And then the raising and lowering metrics is trivial. You just raise and lower metrics indices in the obvious way, which is manifestly positive definite. But the real meat came from the fact that if you try to write the Ricci flow as a gradient with respect to the Einstein-Hilbert action without the dilaton, you have to use an indefinite metric on field space. But in the story with the dilaton, which you then maximize, you get a positive definite metric, the trivial one that I used in these formulas. I see Igor has a question.
Yes, thank you. Thank you very much. I have the following question. Consider two-dimensional sigma model. The question is about mathematical status of this model.
I can't quite hear you. Two-dimensional scattering?
Two-dimensional sigma model.
Yes.
In infrared. Does this model exist?
It exists as a true quantum field theory when the flow is ancient in Perlman's language.
No, I mean in infrared, it seems it does not exist.
Oh, no, in the infrared, let me give a physicist's answer. If the existence is purely a question of mathematicians worry about the Ricci flow. The Ricci flow doesn't always exist into the infrared. However, a physicist's answer is that if the field theory exists, which is only an ultraviolet question, then the model exists in the infrared, but we have trouble understanding its physical properties. So, for example, in Polyakov's case of the round sphere, the model exists because it's asymptotically free, but the infrared behavior is hard to understand. Polyakov conjectured, and it's believed and supported by many arguments, that the model becomes massive in the infrared. It develops a mass gap. What mathematicians say is merely that the Ricci flow causes the manifold to collapse to a point at finite time. The collapse to a point is believed to be a classical version of the fact that the model becomes massive. However, in general, infrared questions never cause a model to not exist. They cause the physical properties to be difficult to understand. Whether the model exists is purely an ultraviolet question, and the physicist's answer is that the sigma model exists when the flow is ancient.
Okay, I have similar question concerning QCD. What do we learn about QCD in infrared from this analogy?
We learn only what Polyakov said, that the analogy suggests that QCD is massive in the infrared, but we don't learn anything rigorously about QCD. Are there any other questions?
Thank you.
Any other questions? Okay, since there are no more questions, I'm going to use the remaining time, which I guess is at least 10 or 12 minutes, to explain a more specific motivation. That had to do with a particular example of ADS-CFT duality. From the original work on that duality, two of the original examples involve type 2b superstring theory on ADS3 times either S3 times K3 or S3 times T4. ADS3 is the Lorentz signature version of hyperbolic 3 space. These are examples with a lot of supersymmetry because T4 and K3 are hyperkähler manifolds. And the duals are known in these cases. The dual of type 2b on either of these spaces is a supersymmetric sigma model in which the target space is instanton moduli space on T4 or K3. The gauge group is UN, and there's also an instanton number, so there are two integers, and they are related to the string coupling constant and the ADS radius of curvature. However, there's another superficially similar example with even more supersymmetry that's been less understood. This is type 2b superstring theory on ADS 3 times S3 times S3 times S1, which has been studied going back to 1999. I've listed the papers that I found more useful. The dual isn't known for sure, but there's been an interesting conjecture that the dual is a sigma model with target the moduli space M of instantons on S3 times S1. For the conjecture to be true, the relevant geometry of M has to have an important and topologically non-trivial B field, with H equals dB being non-zero in the third homology of M. One can show that this third homology is isomorphic to Z, so therefore H has an integer level. That integer level has to match one parameter of the supergravity solution, and two more parameters match the rank of the gauge group and the instanton number. So that's the conjecture, and I've been exploring in more detail whether it is viable. Now, in many examples, if a 4-manifold M has a certain kind of geometry, then the instanton moduli space curly M1M has the same kind of geometry. For example, Kähler geometry on M leads to Kähler geometry on curly M by a theorem of Donaldson and Uhlenbeck and Yale. And hyperkähler geometry on M leads to hyperkähler geometry on curly M by a slight extension of that theorem. That second remark is important for the better understood dualities involving K3 or T4. S3 times S1 with its standard round Riemannian metric with any ratio you want of the two radii has an extremely rich differential geometric structure, which is different from that of K3 or T4, but in a way is just as rich. It's longer to explain, though. First of all, the tangent bundle of S3 times S1 has two natural thought connections, nobble plus and nobble minus, that are metric compatible with equal and opposite completely antisymmetric torsion. One in which the left invariant forms on S3 times S1. Well, you see, S3 times S1 is a group manifold, SU2 times U1. So it makes sense to talk about left invariant forms. One connection leaves covariantly constant the left invariant forms. One leaves covariantly constant the right invariant forms. You can show that both of these connections are compatible with the round metric. And they have torsion. They have completely antisymmetric torsion, which happens to be the volume form of S3 times 1 or minus 1 for nobble plus or nobble minus. Moreover, S3 times S1 can be endowed with two different hypercomplex structures, one which is covariantly constant for nobble plus and one which is covariantly constant for nobble minus. What's a hypercomplex structure? Well, it's a triple of complex structures I, J, and K satisfying the quaternion relations. So a hyperkähler manifold has one hypercomplex structure, but S3 times S1 actually has two hypercomplex structures. Well, actually, it has more than two, but it has two that are useful here. So K3 and T4 with their hyperkähler metrics have one hypercomplex structure. The standard round metric on S3 times S1 has more than one hypercomplex structure. Sorry, when I say it has more than one hypercomplex structure, I mean for which the round metric is Hermitian. It's Hermitian for each of I, J, and K. And moreover, I, J, and K are covariantly constant with respect to either nobble plus or nobble minus. Which one depends on which of the two hypercomplex structures you pick. Finally, there are the left and right actions of SU2 on S3 times S1, preserving the metric and connections, one of which leaves fixed one hypercomplex structure and rotates I, J, and K for the other and vice versa, for the second, for the right action of SU2. So this S3 times S1 has this rather elaborate differential geometric structure, which is too elaborate, as you saw, to be described in just one or two sentences. The structure doesn't have a name, but we could call it large n equals 4 structure. The large n equals 4 structure of S3 times S1 is related to the fact that a sigma model with that structure, and with H equals dB being the torsion, has a symmetry known as the large n equals 4 superconformal algebra that was discovered in 1988. It's a rather elaborate enlargement of the perhaps more familiar Virasoro and super-Virasoro algebras. For the duality conjecture relating strings on this space to instantons on S3 times S1 to be correct, it has to be true that the moduli space of instantons on S3 times S1 has what I've called large n equals 4 structure. Parts of this have been demonstrated in the literature by various authors, but I've been completing the story. The details are a bit too long to fully explain now, but I do want to draw attention to one point, which will relate to the main point of the lecture. It's long been known that for supersymmetric sigma models with torsion, there is a potential gap between scale invariant and conformal invariance. If one computes the beta functions of a sigma model with the differential geometric properties that I'm talking about to the instanton moduli space, if one relates the beta functions of a sigma model with the properties such as this instanton moduli space, you find immediately the appropriate properties for scale invariance, but it's not obvious by any local differential geometric properties why conformal invariance would hold. All arguments for conformal invariance are in some way global. It turns out there are several ways to prove conformal invariance. Some of which are related to things I've explained. After making a certain perturbation of the model, you can invoke Polchinski's abstract argument, which I didn't explain. You can rely on the Perlman-Stahl argument, which I did explain. But here one runs into some tricky issues involving reducible instantons. In the Perlman-Stahl argument, we needed to know that the Schrodinger equation we ran into had a unique non-degenerate positive eigenfunction. And that was not something you could see globally. That involved some locally, sorry. One could not see that locally. It involved some global properties of the target space. Finally, it's possible to make the argument using some detailed differential geometric properties of the moduli space M, and some facts worked out in my paper with Papadopoulos. But again, the argument uses global properties of the moduli space. So with this kind of geometry, local differential geometric properties only lead to scale invariance. And I believe all proofs of conformal invariance use some global arguments. So at any rate, I hope most of you have found one part or another of what I've explained to be thought-provoking. And I want to thank again the organizers for this invitation, and to say that I'm very pleased to have had the chance to lecture at this conference in honor of Ludwig Faddeev, whose work was so influential in our field. Thank you very much.
Thank you very much for beautiful and inspiring lecture. Now we'll take questions from the audience. Any questions? Then maybe we'll take questions from the Zoom participants.
I don't know if there are questions in the lecture hall, but I see at least two in the Zoom audience. One is by Hasib. Go ahead, please.
Thank you so much for your talk. I have a question about the first part of your talk. If I understand correctly, that you have said the proof of the reversibility of the Ricci flow in 3 dimensions is still an open problem.
No, for the irreversibility, there's a proof, not quite as strong as what's known in 2 and 4 dimensions. The proof is by Horacio Cassini and his school, and it uses strong subadditivity of entropy. In 4 dimensions, there's a more sophisticated proof that's somewhat similar in spirit to Zamolodchikov's, but in 3 dimensions, there's a completely different proof. Sorry to interrupt you there. What were you going to say?
What is the technical complexity of this proof?
In 3 dimensions?
In 3 dimensions, yes.
It really requires a different lecture. So I can tell you what function is Well, okay, I can tell you what's proved. If you have a conformal field theory, then its partition function of the three-sphere, a three-dimensional conformal field theory, its partition function of the three-sphere is a well-defined number. If you have a renormalization group flow between two conformally invariant theories, there are two well-defined numbers, one in the ultraviolet and one in the infrared. It's proved that the infrared number is less than the ultraviolet number. And that is what's proved in 3 dimensions. Nothing more than that is proved. That's less than what Zamolodchikov proved in 2 dimensions. That was proved by Cassini and his school. I don't offhand remember all the authors. And the proof is quite sophisticated. It's lovely. It would have made a beautiful lecture, but it's very, very, I don't think I can explain it briefly. Zamolodchikov's proof in 2 dimensions is more explainable in a short time. And the 4-dimensional proof is similar in spirit to Zamolodchikov's, but more complicated.
Thank you so much.
Sure. I do want to say, though, that for relating scale invariance to conformal invariance, there is in 4 dimensions an argument that's closely related to the 4-dimensional proof of this version of the C theorem. But in 3 dimensions, no one has shown a relation between scale invariance and conformal invariance in 3 dimensions, which is actually an important case for statistical mechanics. Okay. Let me turn next to Anton, who didn't ask a question before. And I see you have a question now.
Yeah, thank you for a nice talk. I have a question about those structures on S3 times S1 and on the corresponding moduli space that you mentioned. So how are they related to generalized geometry, right? Generalized complex structures and various stuff of that part of mass. Is it more or less in that spirit? If you can say just a couple of words.
Well, if you ignore the two SG2 actions, then this has been called generalized hyperkähler geometry.
And together with those SU2 actions?
It doesn't have a name I'm aware of.
Okay.
Large n equals 4 structure. But anyway, when I started trying to prove that the instanton moduli space had large n equals 4 structure, I thought what I had to do relative to the literature. There are 2 obvious SU2 actions that come from the SU2 actions on S3. Those will obviously act on the moduli space. I thought I was going to have to prove that the 2 SU2 actions were covariantly constant for the connection with, for the connections. I found that there were more gaps about what was known about this moduli space, so I've had to do a little bit more, but that was my original idea of what I would do. And then, of course, there was the question of whether the model is conformally invariant and not just scale invariant. But I've explained the background for that. Did that answer your question, or is there a further question?
Oh, of course, I would probably need to look at the paper. That would give more impressions. Thank you very much.
Okay, sure. You're welcome.
Any more questions? If not, thank you very much again for the beautiful talk. Let's thank again.
You're welcome. I'm sorry, I think there actually was one question at the end, but Igor had a question again.
Yes, thank you very much.
Sorry.
What's your opinion, Edward, about semi-classical gravity, which is usually used in the context of information paradox? It seems there are ghosts there.
Yeah, I don't have anything new to say. I will say concerning the what came up in my talk, that I am intrigued about the analogy between what Perlman did and the Yamabe problem. And I've wondered if the solution of the Yamabe problem would say anything about semi-classical gravity. But because the theory of the Yamabe problem is relatively complicated, I'm pessimistic. That's all I have to say about it, but thanks for the question.
Thank you.
Sure. Okay, I'm sorry for continuing.
Thank you very much. Beautiful.
Sure.
Thank you.
Okay, thanks again for the invitation, and all best for the rest of the conference.